Okay. Hello everyone. Welcome to the what used to be irregularly scheduled streams, and now maybe it's gonna be more regular. So as usual, if something is wrong with the sound or whatever, please write in chat. But we streamed a couple weeks ago and it was fine, and it's the same setup, so hopefully things are going to work fine. This is going to be mostly a writing code stream. Let me talk briefly though about kind of why. So there's this project that I've been running since a while ago, since like 6 years ago, where we did a lot of work to explore the rendering of sort of, I would call it geometry heavy scenes, except that of course we were kind of limited to, we just had an object that we would instance like a lot of times. This is all written in Vulkan. There's been like 21 streams so far, so this is the 22nd one. And we started from just sort of basic Vulkan mesh rendering, and then quickly got into mesh shading and occlusion culling and some Vulkan stuff and more culling and even more culling. And on the last stream, we kind of had to rewrite our entire cluster culling pipeline to stop using task shaders. And at this point, it feels like we are in a pretty good spot as far as sort of geometry rendering is concerned. There's like one more thing that's like inefficient about our current pipeline, or not optimal maybe about our current pipeline. We use a vertex that has some amount of bytes. Like this is our vertex structure. It doesn't even have tangents right now. It's okay, but it could be better packed. So there's some compression stuff that we might end up exploring, but we are kind of at a 90% of, like a 95% maybe even, of a good geometry pipeline. It's not production code per se, but I suspect that a lot of this would kind of scale to a production renderer. Now, there is a bunch of stuff that we kind of haven't talked about at all. When we started this whole thing, I think the motivation for me to even start this like 6 years ago, I think NVIDIA came out with the 20 series and it had mesh shading, and I wanted to explore this. Since then, there's some other things that have happened in the graphics world that I kind of never even tried, like at work or in personal projects. And it feels like I still want to try them. And so I kind of want to explore them as a part of this project. And so because of this, I'm going to stream the whole thing as usual, because that's how this project started. Specifically, the two things I'm kind of interested in are bindless and ray tracing. Bindless is a different way to bind resources to the shaders to get access to the resources in the shaders. Bindless is not particularly tricky. In fact, it shouldn't be. In fact, this is kind of the point. Like it should simplify the way how we manage descriptors and how we communicate them to the shaders. But I haven't really used the relevant Vulkan extensions ever. So, it would be interesting to do, but bindless is not really useful for us right now. Bindless would be really useful for us if we had materials with textures. Now, once we have materials with textures, the other thing I want to understand way better than I do right now is ray tracing. And I talked about ray tracing on some previous streams that were not related to this project. I'm not excited at all to this day about the whole, there's like kind of two halves of ray tracing. There's this whole like material stuff around ray tracing where you build like a complex pipeline with a bunch of different object types and set up all of these ray sort of, not callbacks, but like kind of when different invocations should happen, etc. I kind of don't care about this. I think we need better mechanisms to do this kind of stuff. There's some better mechanisms that people are building now, like word graphs, but I kind of don't care. But what I do care about is the underlying sort of hardware and software that is the raw. Here's a bunch of triangles. How do we trace array through them? And this can be useful without all of the other stuff. And so I don't really have super solid plans for what we are kind of going to be doing here, but I think the general theme is, can we get from where we are right now, where we can just render a bunch of triangles on screen, to the place where we render a scene on screen with materials, lights, lighting, and shadows and all of that stuff. Now, to remind you all, what we have right now is this. So the only thing we can do is we can take an obj file, which is what we support. Obj files in theory have materials and stuff, but we aren't using that at all. And also, it's kind of a not, I think obj files work well when you just have geometry with like very simple attributes like normals and texture coordinates. But once you go further, you're really pushing the limits. And so we can load this, and then we can instance this a whole lot, and then we can render all of this stuff very quickly because we have a bunch of culling things and we are efficiently submitting geometry to the GPU, and all of this stuff works really well. What I want to do, what I want to get, is from this to something that looks more like this. Well, not... So I have a scene. This is the classic Amazon Lumberyard Bistro scene that I have in Blender. Blender has various display modes that range from just textures basically to like textures with lighting and stuff. This is kind of where we are going, right? So like the goal would be to get something like this. But I've spent my entire career in game development working with shadow maps. I don't want to go there at all in my spare time. So kind of instead of, you could render this with fully traditional raster. And there's no real issue with that. You could also do point light sources and all of that stuff with traditional raster. But for example, there's this recent work that Epic people have been doing on megalights, and there's an NVIDIA presentation, I think, called Lights from a few years ago. And that stuff feels like maybe it's the future, where like in 10 plus years, that's kind of how we do things in real time everywhere, like in every game. So that's kind of where I want to go, but I still want to keep the rasterization portion because it's interesting. We've written all of this code for the last many years. So the plan would be render the scene using rasterization, but then use ray tracing to actually do complex effects like shadows and lights. Lights you could do obviously without, but if you have a lot of lights, with shadows, then you might just want to do ray tracing. So anyway, that's kind of the overall plan. But given the fact that the only thing we have right now is an obj file renderer with like a lot of instances, it's going to take us a while to get there. So we're going to start slow and small. The first thing we are going to do, which is what we're going to do on this stream, is try to render the scene. Instead of just a bunch of files, and load it from glTF instead of obj. I've spent a lot, last 4 or 5 years maybe, working a lot with glTF. I'm kind of, I guess, an expert in a sense on glTF. Like, I authored an extension and a half or something like this. I have written this tool, glTF pack, that a lot of people use to process glTF assets, etc. So I know the format really well. I kind of like it. Usually the way glTF is useful in serious real-time production workloads is not as a runtime format necessarily, but sort of as an interchange. But we're just going to use it as a runtime because we do a bunch of this geometry preparation, like when you load the scene anyway. So we'll start with that. We'll see where this takes us. So I have the scene. I've spent some amount of time yesterday like wrestling with this scene is weird because the original version of this scene has a bunch of inefficiencies and a bunch of material issues. NVIDIA has a copy of the scene that it looks like they did a bunch of manual work to fix it up. It's instanced much better. It, I think, has material fix-ups. It has the interior like inside this sort of bar or restaurant or whatever this is. I think it originally came as like 2 separate files, and this is one file. So anyway, this is what I have. This is basically just an NVIDIA asset that I got from. I might link it later. It doesn't really matter as much, but it's like from a GitHub repository with NVIDIA samples. You can get the scene, and then I had to process it a little bit to add a light there and camera. One issue with our current code, though, with this code, is we actually don't quite have a camera. When this code was originally written, and I intend to keep doing this, we kind of cut as many corners as we possibly could to get things running as quickly as we can, and then we fixed the problems when they needed to be fixed. The problem of having a camera that can be moved has never come up. And so because of this, we don't even have a view transform. We only really have a projection matrix. So we'll have to add that today to even be able to like render that, right? And then, we'll see if optimally we would also load textures from files today, but not actually plug them in, because plugging them in requires bindless exploration, which, I'm sure that there's no way we can do this today. But anyway, so the plan is load the scene from glTF. We are going to keep all of the existing code that deals with OBJs as well. One of the things about the scene is it's actually a small scene comparatively from the geometry complexity perspective. The scene has 1.7 million triangles. In frame right now, we are rendering 12.5, so that's 10 times more. And that's with level of detail and occlusion culling, and this is just the visible frustum. If we disable culling, hold on, is it not? The triangle count is busted when I disable culling. That's strange. Anyway, if that is suspicious. Whatever. So there is 36 million. Oh, C disables occlusion culling maybe. At some point, maybe we'll also hook up like DRM GUI or something like this, because there's so many key binds now that I forget which button does what. But we render 36 million without cluster occlusion culling. 49 without occlusion culling, and then 100 something, or is it a billion? I don't even know. Like a lot of triangles if we disable level of detail. Yeah, like 1.4 billion triangles if we disable level of detail, and that's even still with the frustum culling, so it's actually more. So from the geometry perspective, we want to keep this mode because this allows us to really stress test all of this like mesh shading stuff, etc. Right? But when you have a glTF file as an input, I want to render it. I want to use the camera that's in the file if it's there, and then eventually add like lights, textures, shading, and all of that stuff. So that's the plan. We are going to see how much we can do today. At the minimum, I want to render the geometry. So at the minimum, I want something like this, where you just have the geometry rendered from the camera that is in the file, but like no textures, no nothing. So that is the plan. And then, like in the future, we will see, the stream will generally happen on Saturdays in this time frame. I don't have every Saturday in this time frame in the next month or two free, so we will occasionally like skip days or whatever, but skip weeks or whatever. But we'll see what the schedule is like. So are you planning to use descriptor vk.ext descriptor buffer? Yes. Did you manage to figure out Wayland glFW compatibility with RenderDoc? So no, or yes. So right now I'm rendering with Wayland. You can see because of the window title, it's kind of like weird. This is actually something you can toggle and then rebuild, and then it will use X. So in this mode, RenderDoc works. I actually have it downloaded today, and I tried it, and then it works. We might use it if we need to. The issue with using X, so like the reason why I don't want to just do this is there's like weird display resolution issues when you render with X instead of Wayland, where you don't get correctly sized pixels in your frame buffer. So I think if we need RenderDoc, we will be able to use RenderDoc clearly, but unfortunately it's not exactly like, it's not super friendly right now. By the way, one thing I wanted to show on the last stream, but there was no way to show it in the last stream, and now there is, because you see the scene in RenderDoc, is the effectiveness sort of occlusion culling, which is kind of interesting. So RenderDoc has this geometry view, and you can see here clearly there's a ton of triangles on the screen because there's a lot of these like small instances far away, right? But there's this big blocks where there's nothing rendered behind the actual mesh. So like here, for example, in the bottom right corner, which is probably, you can't see because it's like occluded by the stream. So this and this region and this region, these are all sort of examples of cluster occlusion culling and also mesh occlusion culling working really well. There is some amount of geometry on the borders here that is rendered outside of the screen. This is kind of fine. It's a byproduct of, we do cluster culling against frustum, so in theory you would expect very, very little geometry to overhang. But our test of the sphere versus frustum is slightly conservative. B, the sphere, that's the bounding sphere of each cluster, is an imperfect representation of geometry. C, there are sometimes clusters that are sort of split. There's like a cluster, there's like a few triangles in the cluster in one part of the mesh and a few triangles in the other part of the mesh. In these cases, you can have like a little bit more geometry that's rendered outside of the screen bounds. But like in general, that's fine. There's very, very little overhead in the scene, I suspect. So it's probably okay. Oh, and by the way, off stream at some point, I think last week I upgraded, it must have been last week, I upgraded to the latest Mesh Optimizer version, which is great because it made like a bunch of stuff better without changing any of the code. So essentially this demo today works way better than the demo 2 weeks ago or whenever we streamed, just because of the Mesh Optimizer upgrade. So that's cool. Anyway, that is it. So we are going to start writing code, and then I will occasionally look at chat. Load textures without blocking. This is possible in Vulkan. We will not do this for a while in this series. We compile all of the shaders ahead of time, and the textures for now we will also load ahead of time. This is possible, maybe at some point we'll do this, but it's just not super necessary for us right now. Mesh.compression compression post from AMD, yeah, I'm well aware. They have a paper, the paper cites Mesh Optimizer, which is fun. We will not implement that paper. I want to find like a different way to do some of this stuff, but yeah, sure. If you haven't read this, there's a good paper from AMD on mesh compression. So glTF. For people who are not familiar with glTF, it's a JSON file that stores a bunch of the scene information, and then the actual geometry and textures are stored in binary blobs. There is a library cgltf which we are going to be using. This library is written by Johannes Kuhlmann. It's a C library, not C++. Of course, you can compile it in the C++ application, which ours is. It's good. I would recommend it for production use. This is the library I use in glTF back. It's used in a bunch of other places. Of course, I'm biased because if you look at the contributor list, I contributed a little bit of code to this library, but I think it's like legitimately a good library. It's pretty fast. It's not the fastest because it uses a simple JSON parser instead of like CMD JSON, but it actually doesn't matter almost ever. Like it's almost always as fast as competitive libraries, and it's simple. So you can plug it in and you can very quickly start using the resulting file, the resulting data. The one thing is when you work with this library or when you work with most other libraries, you kind of have to understand the glTF construction. So you have to have read the glTF spec. I will try to write code fairly quickly on the stream because this stuff is not like Vulkan related per se, right? So I will not go into a lot of details other than just things that come up as I write the code in terms of like how the glTF stuff works, right? It's all in the spec. Anyway, so I actually already have added a library to the project couple days ago because I wasn't sure if I want to do this on stream or not, but now I decided I want to do it on stream. But the integration is very, very simple. We just added a Git submodule, and then we added the include path. And then there is this library is structured as many other single header sort of C libraries are, where you have to have a source file where you compile this code. STB images exactly like this, etc. We already had a source file that compiled like fast OBJ, so now it also compiles cgltf. So that's it. That's kind of like the entire integration. I mean, there's also like non-CMake changes that are the same, but literally it's like a couple lines here, a couple lines here. And there's no other code that's glTF related, and all of the other stuff we are gonna write now. All right, so I will occasionally look at chat, so if people want to ask questions as we go, please do. And I will mostly ignore questions that are off topic because I want to get a bunch of stuff done on the stream. So this scene is in a bistro folder. I might publish this on GitHub later, we'll see. I'm not sure what the license applications are, but it's basically an NVIDIA repository that I mentioned that I got this from, which is a good version. And then I added a camera, I added light. I did some stuff with textures that if we get to textures I'll talk about. And that's it. And then I also have a copy of this, which is, so this is like the original scene that I kind of hand patched. And then also this is what you get from Blender if you import it and then export it back, which it's probably roughly the same, but it might not be. We will load this. So because we are going to be using the library, the fact that it's like a JSON file, etc., is not like super material. But very briefly, ignoring the materials and textures and stuff for now, because I'm not sure we'll get to this. So glTF file has meshes, and then mesh has like normals, positions, tangent, text coordinates, etc., etc., etc. So we're going to get this out of the glTF file and put this into our data structures. And then it has a scene graph, which is a hierarchical sort of set of nodes, right? And then for every node, you might have a mesh attached to it. We are not gonna use the graph itself because we don't need like animations or whatever right now. We are just gonna take all of the mesh attachments and then compute the world space matrix for this, and then use all of our existing stuff that can do multi-instance with that. Fortunately, some time ago, like a while ago, We have implemented support to render multiple meshes, like despite the fact that right now you see the same mesh getting instance. Oh, let me go back to Wayland. Despite this, we actually do support multiple OBJ files, hopefully. Let's see if that's true. All right, these meshes are at different scales, but like clearly there is more than once. Yeah, more than one. Yeah. So the fact that we have this will make our life simpler because hopefully the rendering code is mostly fine, with the exception of the thing I mentioned, which is we don't support view projection for a camera like as a thing. So, all right, let's go. So let me open the terminal. Maybe put this here. All right. So our goal is that if you specify a command line argument as a glTF file instead of an OBJ file, then instead of doing the thing that we are doing right now, we are going to load that and then from that sort of load the geometry and stuff. So let me look at. Oh, one other thing I forgot to mention, somebody asked about the XT descriptor buffers. So we are going to use this. I'm not sure if we'll get to this today, but one thing in general, we'll start being a little bit more aggressive about like requiring certain features. Like right now, this code requires very few extensions and val conversions and kind of has fallbacks for all of the various things that might be missing. I'm going to be removing them sometimes on stream, maybe sometimes off stream, like gradually, because it's just going to make the code like easier to deal with. This is not meant as a render that you ship. This is meant as a project that demonstrates production-ready techniques, and also for me to have some fun code to write, if I'm being honest. So, but like none of that probably will happen today. So the first thing I want is like this mode, right, where instead of just having a bunch of objects, if the input is a glTF file, and for simplicity, we might only require. We'll see. Right, so what I want is this. The first thing I want is so if you have hold on, I need to like refactor this code a little bit because it should be useful for both modes. So the glTF path will populate meshes and draw call information, which is the objects that we need to draw, into the structs. And then if that didn't happen, then we will fall back to our old code that like instances stuff with some fixed hard-coded parameters. We do need to extract. This is the code that some of this code we might rework later, like I didn't get to. That's annoying. Hold on. All right. Okay, we have some code here that like allocates bits for cluster visibility. You can, this has been like described sort of on stream. I think it just zero initialized, this is fine. So you can go back to previous streams if you don't know what meshlet visibility counts are, but we might just rework some of this in the future. Oh, we need draw counts for some reason. But yeah, let's just refactor this a little bit. And then, right, so we have this thing called draw distance, which we are going to keep for now, which is like a hard-coded far culling plane. 200 is probably not enough for the actual scene, but for now, oh god, what else? Draw count. Okay. Okay, so I think we split stuff reasonably well. So now essentially, if the input is a glTF file, then instead of, I might just, for now we will only support one glTF file to make it easier. So we'll need RNG here. What even is this? Oh, this is the global. Okay. Okay, this is fine for now. Okay, so when the glTF file is an input, which we are gonna call, so I guess, should we, I don't want to support, is it easy to support multiple scenes? It's gonna be a pain, because if the scene has two cameras, what do you do? Let's just say that we will not support a hybrid mode for now, and if so if we have exactly one argument, C is like annoying sometimes, so let me okay. All right, you know what? All right. We are like not really using like strings and string views and all of that stuff, which is cool, but this means that something as simple as, oh, is this file a glTF file, is like painful to check. Okay, so okay, and then return false. All right. Okay, so our actual file that we care about is, where did I put it? Bistro glTF. And then, oh, is there a way for me to, alright, that's fine. It's painful because like I have the stream window like on the bottom right, but it's fine. So the main thing that we have is, the main thing that we are targeting is to be able to actually load the file. So cgltf, I don't remember the API by heart, but it has like this, okay, GitHub Copilot is sometimes useful and sometimes stupid. So the way this API works is you call one function. It's sort of two functions to three functions, depending on what you need. But you call a couple functions, and then you just have all of the data in memory, and then you can do whatever you want with that memory, with that data. I don't remember if options... Yeah, okay, so you have to specify them. Okay, so we are going to parse the file. And then success or something like this. Yeah, okay. And then when you parse the file, when you call parse file, it just loads the JSON file. It doesn't load the buffers that are attached to it. And we will need these buffers to be able to actually sort of render geometry. So we are going to do that. And then same thing. And then the other thing that's very useful is the cgltf validate function. So there is a bunch of cases where the input file will have weird issues. Maybe it has indices that are not in the right place. Maybe it has some weird format that's like not supported by the specification, etc. Sometimes you don't want to do a validation on the file, but most often you do. And once you validate the file, it should generally be safe to use. It's not 100% like the case, but generally a good practice when using the library is the code that I'm writing right now. So you parse the file, you load the binary buffers, you validate, and then you declare victory. And then, of course, you free the file, which all right, fine. Whoa, what happened here? Date is like a weird name perhaps, but I think it's fine. Okay. Okay, so we loaded the scene correctly, we validated it, like everything is fine. This means the library works, right? But then we are gonna return false until we write enough of this code to be useful. Because otherwise, actually, hold on. I probably should do... Oh no, this is fine. Whatever, it's cool. At some point, like some of this code is going to be a little bit like single use in the sense that we are testing on one scene. Ideally, we test on a bunch of different scenes, but we don't care about any of this right now. So the file has the two things we care most about right now are meshes and nodes. Meshes are geometry, and then nodes are sort of the places where the geometry is attached. And then we care about the camera, but we let's just load geometry for now, and then I'm not even sure what will render if the camera is kind of in its default like origin position, but whatever renders, renders. So maybe, actually, hold on. What I will do is I will show you guys I want to attach the debugger and kind of just show like what the structure looks like. All right, so we loaded the thing, we validated the thing, and then we have, oh, I forgot to free, I will do this momentarily, but then we have in the bottom left the structure. And it's a bunch of like pointers and arrays and all of this stuff, right? So it has the asset, whatever produced the asset, the version of the file, a bunch of meshes, somewhere meshes count 551, so 500-ish meshes, and then nodes count somewhere, you probably can't see nodes count because it's behind the screen, but it's like 5, 9, 10, 6,000 nodes. and like a bunch of other stuff. So and from then on, you just look at the data in the header, and then you say, okay, cool, mesh has like indices and vertices, so parse those, etc., etc. Fully handling all of the possible kind of cases is a little bit difficult with glTF because it's a very general format. cgltf helps with some of this, but not sort of fully. For example, a mesh may have no index buffer. We currently expect a mesh to have an index buffer. We could like generate an index buffer, but I think for now we are gonna again cut as many corners as we can. And then, when these restrictions become important to unlock, we will like unlock these restrictions. All right, let me briefly look at chat. So if you want to use fast glTF, you're free to use fast glTF. I would not recommend it, honestly, because it's harder to build. I think it's like C++ 17, if I remember correctly, maybe 14, CMD-JSON, like all of this stuff. But like again, if you want to, it's fine. My recollection is that cgltf is used sort of reasonably widely. tinygltf is more popular, but tinygltf has some annoying performance and sort of code quality issues. But again, like I'm biased. I've used cgltf a ton. So of course I would recommend it. You can use any library of your choosing. You might be writing this code in Rust, in which case I think there's a glTF-rs library that you would use instead of any of this code, right? I'm sure there's something for Zig, etc. So pick whatever library you want. This project generally tries to choose libraries that are as close to C as possible to not have to deal with any of the C++ stuff unless we decide we really want C++ features and, like containers and whatever. But to each their own. My pick would be cgltf, but fastgltf is fine. I just don't know how many. Like cgltf is used in Filament, which is Google's renderer. What else? Godot has like a custom one, which because of course. Raylib uses cgltf. Anyway, there's like a bunch of engines that use cgltf. It's pretty neat. But yeah, fastgltf is fine. I don't think it's like a problem if you use fastgltf. It's my personal preference would be cgltf. Okay, so we have loaded everything except that we actually need to extract the data. So let's do. We have, and the code that we are going to be writing today will have a bunch of annoying duplication because we are going fast. Ideally, we would refactor some of this later, but for now, we're just gonna do like the simplest thing possible. Okay, so we need to load the meshes and we need to load the mesh attachments, aka nodes. And I'm trying to see how much of this code. Oh, this is not too bad. This is not too bad. Actually, we will refactor. Sometimes it's better to refactor the code as you are writing it, and sometimes it's better to refactor it like later. I usually kind of do whatever makes sense in the moment. So what makes sense to me in the moment is this. Oh, but it has. Okay, this might be fine. Okay, so Yeah, okay. You know what? I think it will be faster if we just copy the code, change the code, and then extract similar pieces compared to thinking about, oh, do we need this? Do we need that? We'll just write a function that will be perhaps useful in the future. And then my code style is all over the place in this project, actually, now that I think about this. This is the problem of having many different projects that have started in different time frames. All right, fine. So the reason the pointers are like non-const for a reason. It's because essentially I want to keep doing some data optimizations in place. If you don't know what the mashup stuff that is like here is doing, all of this was covered very, very early in the stream series. So I want a function that will just load the mesh from the input geometry, which is vertices and indices. So it will optimize them for various targets. And then, and then it does some, why though? What does it do with, oh yeah, right. It decompresses the normals to be able to do simplification. This will not work. Okay, and then computing the radius, LOD. Okay, you know what? This would be faster if we like use vectors everywhere, which is fine. Okay, so then and then this is actually fine with no. Oh. What the heck? Ah, okay. Cool. All right, let's actually keep it like this for now. Wait, it's not what I need. All right, so vertex count somewhere. Oh, okay. Okay, actually, I think we should be able to use this code now in this other function. So this function is now gonna load, remap, and then we extracted like everything else in the function. Okay, So we did end up doing refactoring as we go, which is fine. Okay, so now we have a function that without going through the obj parsing path, which is this code, can just load data from glTF, not from glTF, but just from like a vector of vertices and indices. And then it still does all of the processing for mesh flats and caches and simplification and all of this stuff. So now we just have to call this function appropriately. And then actually it's infallible. So that is very cool. Or we might need some assertions or something, but for now, let's just do it like this. Okay, so now we are almost ready to we are probably basically ready to just call this function. So cgltf has an array of meshes. I don't know why something, in theory, I have code completion, like not Copilot stuff, but like the actual IntelliSense like completion working. Oh my God. No, this is not what we are gonna, no, this is not what we are gonna do. Oh my God. It's actually not completely wrong code, but it's not completely right code. Right, one thing I forgot about is that glTF meshes are actually composed of primitives. It is annoying that glD doesn't work. Primitives count, because I don't remember the API by heart, and it would be nice if this worked. Okay, so glTF allows you to have multiple kind of submeshes in each mesh. It is not hard to deal with that, but we can't even test it because all of them have one right now. For now, let's just keep this. This is obviously not production code, but we will restrict this in the future. And then the way meshes are organized in cgltf is, so there is a struct with primitives, and then there's a bunch of extra stuff. This is mostly for morph, like blend shapes, morph targets, which we don't care about. So it's just an array of primitives, and then each primitive is an index buffer, material reference, which we currently don't care about, but this will be useful in the future. And then vertex attributes, which we need to actually extract data from, and then a bunch of stuff we don't care about. And then also glTF supports like non-triangle meshes, which we obviously will not support. So we will have some restrictions on the content that we can parse, but that's fine. And then accessors, so attributes are vertex positions, normals, etc. This is just a type which can be like position, etc., and then data, and then all of the actual buffer data in glTF is accessors. We don't actually care how accessors work, because cgltf has convenient functions that essentially say, hey, here's a bunch of data in glTF. It's stored in some way. We don't care how. We just want floating point or integer values out of that. And that is what we are going to use. And the one thing I don't remember, cgltf doesn't have this function. I was thinking about this. We should add that. So meshes have like an array of accessors for positions, etc. But there's no, because we have a fixed vertex structure, essentially what we care about is we'll have these vectors that we need to fill, and then we'll call load mesh result. Is this called result? This should be called geometry. Geometry vertices, indices, and then like build meshlets. And then this will load the mesh into all of the structures that we need. So to extract this data, let's see. Doesn't really matter if anything is const correct here, but I guess it's fine. Okay, so we will only support triangles. Man, it would be nicer if autocomplete worked. Why doesn't it work? glD has some issue that I hit occasionally on some of my projects for some reason that sort of can't parse the source. It can parse the source, but it has errors that come out of nowhere that then make it give up on the rest of the file, and I don't fully know why that happens. It's as if, oh, I don't have a compilation database for this actually. This is probably the problem. All right, I will not care about this for now. Maybe I should. There's some way to. Do I just have this somewhere? No. Okay. Fine. There's a way to fix glD, but maybe I will do this off stream so that the next time we'll have better autocomplete. Okay. So we only support triangle meshes. We need an index buffer. Just, you know, certain things are not optional. They're optional in glTF, but in our renderer we need them. And again, we can work around some of this. We can generate an index buffer, etc. But we don't. I don't want to do this right now. And then we need this function that unfortunately isn't part of glTF right now. That essentially says. Let's see. Here's a primitive, and then we want to find an accessor that has, oh, actually, yeah, an accessor, this is fine, that has a given attribute type and index. Okay. I will do it like this. Okay, and this will just make it easier for us to. So a bunch of things in glTF is optional. For example, you might have normals, you might not have normals. You might not even have positions, I guess. I'm not sure if that's true. This is obviously, this is part of why ideally, this is part of why in like a game engine runtime, you usually don't use glTF at runtime, you usually use glTF in your like content pipeline. Because there's a bunch of these edge cases that you just want to iron out. For example, maybe you don't have tangents, but you can generate tangents. Generating tangents takes a while, and it's a complex operation from the code and code runtime perspective, so you don't want to do this at load time. But this is probably okay for what we need. So let's do this separately. We need to load Vertex data and index data separately. And then you need to have at least one accessor, because I think the file is invalid, so this is actually safe. You have to have at least one sort of source of Vertex information. And then we'll just load positions, normals, texture coordinates. We could load tangents, we don't have them in the Vertex yet, so we'll just skip this for now. Obviously, if the mesh doesn't have positions, like it's not really valid, but we will ignore what actually happens if you feed an invalid file for now. So this function that I was talking about, right? Oh, glD worked. Things are weird sometimes with the tooling. Okay, so given the position, The reason why I'm pausing is the vertices are floats, but the normals for us, and we have like quantization basically used in a bunch of places. So we need a temporary buffer. We will need 4 for tangents. So, and also this function can fail, I think. Well, so as I said in the beginning, like generally I think cgltf validate makes sure that all of the consistency guarantees that you'd want out of the file permitted by the spec are there, which means I think that functions like this can fail. But ideally you would like assert a bunch of stuff here. We'll not bother for now. So, oh, and then the other question, right, the correct question is actually, hold on, converts them, assumes, I guess what we should do is just to not run into like weird surprises, we should have 3 floats for positions, 2 floats for texture coordinates, 3 for normals, 4 for tangents. So just to make sure nothing like weird is going on, we will do that. And then we copy stuff to the vertex structure. And then we repeat this for normals and then for texture coordinates. Okay, and then normals we pack. That code is wrong. Why am I using this code? This is wrong. This is not. Man, this was written like a while back. No, but why? Wait, what the heck? Hold on. Oh, no, this code is correct. Right, okay. All right. So we load the normals, and then we will load texture coordinates. There's just 2 floats. And then texture coordinates are packed using half precision format. So, all right. So that's roughly the code that we need. And then for indices, we just need to allocate however much the accessor tells us. And then there is this other function called unpack indices. So I think the way this works is you tell it where to. Indices could be like 16-bit or 32-bit. We use 32-bit, I believe, which is why we basically just need to say, hey, we are using 4 bytes per component, and then that's however many we have. All right, that's kind of it. I don't know if the code even compiles, which obviously it doesn't. So this should be a cgltf function. I'm actually not sure. Maybe I'll submit like a pull request to add this, because it would be simpler if this is like a very common thing that you want in. I think the rule of thumb that I find useful is if you have a library and almost every user of this library needs given functionality, you probably should expose this functionality in the library. So, okay, it's probably not called primitive type, it's probably called type. And then we want const correctness everywhere. And then we want to actually apply const correctness here. Okay. Okay, so we are starting to have, calc size returns bytes, not, we don't even, hold on, this is not correct. We don't care about the storage. So essentially what unpack floats does is it extracts the floating point data out of whatever format it has, but it extracts scalars. So we want to make sure that positions are actually 3 floats. And again, maybe this is actually correctly validated. I just don't recall and I don't want to find out. So I think what we need is num components. What we need to validate rather is num components instead of calc size. And then the code maybe works. It's not super fast, unfortunately, but maybe this is because there's all of these vector accesses that we are compiling with debug right now. Because of this, this was very convenient because we had all of this validation code that kind of could run, and assertions run and all of this stuff. This is inconvenient now, but you know, I will briefly look at performance a little later once we get the code run. So let's actually step through this code. I will look at chat in a moment to see if people have any questions so far. Let's step through this code to just make sure that it's doing the right thing. Okay, perfect, actually. All right, we actually have, we are doing actual work, which is always encouraging. Is it not F? I thought it's F. Okay, I guess it's finish. So let's step out of all of this. Okay. Let's look at the first vertex. Hello. GDB is annoyingly slow with debug information sometimes. Okay, we have a vertex that has a position, a normal, and a texture coordinate. So I think this is good. This means our code is probably doing something reasonably close to correct. We will find out for real once we render something. But this is a good first step. CMake export compile commands equals 1. Thank you. Thank you. So CMake export. And then I guess I run Ninja or something. All right. Let's see. Oh, thank you. Thank you, Kafka. I really don't care about behavior graphs. Sorry. This is glTF was really good until they decided that it should be a USD file format, and then it kind of went south. No, behavior graphs can do Somebody else can do behavior graphs on their own time. Okay, so we loaded the meshes, maybe, and also we have autocomplete working, which is fantastic. Now we need to actually attach these meshes to like something in this, like we need to have something to draw. We just loaded geometry. So geometry is located in nodes, or rather, as I said, there is this node structure. There is this scene graph, right, where there's a hierarchical structure of nodes, and then some nodes can have meshes and lights and cameras attached to them. You could just serialize or like sort of convert from glTF to your own hierarchical graph structure if you have it. If you don't have it, which we don't, then you could just walk over the nodes. And then for every node that has a mesh, you could compute the world transform. And cglTF makes it very easy. It has a function that just computes the world matrix from a node. Whenever you work with matrices and computer graphics, you have to deal with awkward questions, such as, is it row major, is it column major? Nobody knows. The other thing that is worth noting is cglTF doesn't have helpers for this because this is not a thing that comes in every application. But for us, we actually support, we don't even support non-uniform scale. So technically, we will not be able to process some files in glTF format, but that's fine. We'll just like emit a warning or something if the mesh is not uniformly scaled. And then we are splitting the transform into the position and orientation, which is a quaternion. And what we will need to do is we'll need to get from the matrix to the quaternion. Unfortunately, glTF, while glTF has the split structure as well, it does position or translation, non-uniform scale, and quaternion orientation. There's two problems with this. One is you can have matrices in glTF. They have a weird spec that says, oh, a matrix is fine as long as the matrix is decomposable into TRS, which, you know, is good, but you need to actually decompose it. And then the other annoying part is, so if you have two transforms, one is TRS and one is TRS, both have non-uniform scale and rotation. If you multiply them together, you may have a transform that is not decomposable into TRS. It may have skew, which we can't support this, period, right? Because in our case, the draw call is like an in-world space and it just has the rotation, etc. Nor do I want to support it. I don't like skew. It's bad. We don't even support non-uniform scale. So anyway, we essentially need a slightly lossy function that gets from a matrix to quaternion scale position. Do I want to write this function on stream? No. So I'm gonna copy it from glTF back. But let's first go through the nodes and let's like ignore rotations and stuff, and let's just get translations and then just place the meshes, and then maybe at least that's like rendering them, right? So, okay. We only need, well, in the future we'll have to process lights and cameras here as well. But for now we only need mesh. So if there's a mesh attachment, then mesh is a pointer, right? Because cglTF is representing everything as this graph of objects and arrays and pointers between objects. And this is actually a pointer into the meshes array. cglTF has the convenient function somebody contributed at some point called mesh index, where you can ask, hey, I have this pointer, which index in the file does that correspond to? And the reason why that's important is here we processed all meshes in sequence, and for every mesh we just appended one mesh object. And so because of this, right now we have aligned indices between whatever we produced here and the internal glTF indexing. This is going to be different once we fix this to-do comment, but that's going to be an easy fix. So anyway, this is our mesh index, and then basically in general we need to fill this structure. we need to fill transform, we need to fill mesh index, we need to fill this vertex offset, which is kind of a hack, which fine, we're gonna fill it. And then this thing, I just moved the loop like 30 minutes ago into like a separate structure in the file, so that's fine. So really we need these guys. Oh, I guess autocomplete works now, so I should be able to just. All right, so mesh index is this, and then let's do this for now. Do I trust? Problem with Copilot is you want to figure out if you trust it. And I don't. The second problem is there's some. GLM is a pretty good library, but with Quaternion specifically, I think it uses this kind of unconventional, depending on who you ask. Yeah, okay. I don't actually recall if this is correct. This is annoying. Let me use a thing that's definitely correct. Yeah, I guess. Okay, and then this code is broken. So I was saying there's this function node transform world that extracts transform from a node. Transform is a 4x4 matrix, or it's a 4x3 matrix, you know, or maybe 3x4, depending on who you ask. And this function automatically follows the parent chain and multiplies the transforms through. So it kind of takes care of the hierarchy for us because we don't care about the hierarchy right now. And of course, I don't remember, okay, 12, 13, and 14 are the position. Okay, so and then of course we want to actually push it back. All right, let's go. It is not very fast. I know it's debug mode, and we are loading a very large file. It's like hundreds of megabytes, and it's in debug, but I don't like it when code is slow in debug. Okay, so let's just plug this in and see what happens. There is a possibility. I forgot to give the disclaimer. This is Linux. Linux doesn't do timeout recovery for GPU code. Our code is heavily GPU based, and if something is terribly wrong, the stream crashes. This happened last time once, but not because of our fault, but that's fine. This might happen today. If it happens, I think I can restart the stream pretty quickly in like 30 seconds or so without losing the continuity. So that's going to be hopefully fine. Okay, so let's run this. Let's see what happens. Hopefully we have geometry on screen and nothing crashes. We have some geometry on screen. I wouldn't call it a success. All right, so now we will spend forever. So the way graphics programming works is first you excitedly write code for like an hour and everything is perfect and everything works. And then you try to actually run it, and then you see garbage on screen, and then you debug it for like 5 hours. We are not applying the rotation matrix, so we should fix that. I doubt that the lack of the rotation matrix would be as dramatic as what we are seeing right now, but we should fix that regardless. I guess I could use. I'm wary of just using GLM, Quaternion reconstruction functions, because I don't know off the top of my head if the matrices in GLM are like correctly sized, but maybe I should try. Maybe it's fine. Let's look at the matrix for a little bit. I don't think our problem, I think our problem is elsewhere, and I'll have to actually like read the code carefully and then use render doc and stuff like this to figure out why it's broken. but the if somebody has a recommendation, well, I shouldn't be saying that, but I don't love GLM because of what I'm doing right now, because it's like a lot of, it's really good if you want doubles and floats and all of this stuff, but it's a little painful to understand the code if you need to, and we do need to. I think they have a transform thing, which, yeah, okay. Okay, let's see. So this layout is probably the same. It would be unusual if this is non-sequential in memory. So I would guess that the matrices in GLM are the same, like the structure is the same. And now the question is, do they have a Quaternion extraction thingy? Like, is there a way to get from matrix to Quaternion that GLM implements? You know what? I'm just gonna steal code from glTF pack. It's good code. It's based on Mike Day's, I think, derivation. That's very numerically stable. It should work fine, etc. Let me just open this. Okay. Where is it? It's probably in Node CPP. Yeah. Again, don't think this is our problem at all. Because, well, I suspect it's just not. Oops. So this function takes a matrix laid out the same way as cgltf does it, I believe, and decomposes this into translation, rotation, and scale. And in our case, like, we don't handle non-uniform scale, and this function doesn't handle skew because it's impossible to, like, you know, the interface doesn't suggest that it can return a skewed transform, which means that if there is skew, you're gonna have weird, like, rotation and scale, but this doesn't actually matter because obviously we don't even support it. So scale can be negative, I suppose, which we don't believe we handle this either. So let's do let's do this, which is not great, but you know, it's fine. And then again, God knows if this is the right order. And then and of course, well, all right. So clearly we have bugs to fix. Oh, hey. Some of the, oh, I forgot to copy vertex offset. Where is it? All right. That's definitely a big part of the problem. So this is clearly wrong, but I would not be surprised at all if the Quaternion is like, so this function, the decompose transform function assumes x, y, z, w order in the Quaternion, and I think the cgltf GLM interface assumes this weird like w, x, y, z order, which would be basically 3, 0, 1, 2. And I also don't know where the camera is, or like the camera is in some sort of origin that, you know, is like, who knows what should be rendered right now, because we aren't even setting the camera correctly. Well, did this help us? I don't know. I don't know that it did. This actually might be correct, because the camera is in the 0, 0, 0 point. I just don't know where in the scene is the 0, 0, 0 point. And then obviously it's a very weird angle. I suspect it's still incorrect, but clearly the geometry at least is somewhat competent now. So let's, so one thing I want to do is, let's do this. I mean, it would already be let's just so that we don't forget. I would be surprised if this, well, okay then. Let's see. I really don't want to do non-uniform scaling. It breaks a bunch of assumptions. It's not pleasant to deal with. So okay, yeah. The tolerances are just knots. It's like it's fine. Okay. This code is a little rough. I would do this slightly differently, but I just want to make sure there's no cases where things are egregiously non-uniformly scaled, and then, you know, like some things will be slightly off. So yeah, so I don't know if this is correct at all. And you know, I don't want to debug GLM yet, but I don't know if this was correct at all. I would be surprised, because the objects yeah, they're just off, like this 2 yeah. So I think it's pretty clear that the transform needs to be flipped the way I just flipped it, but really until we put the camera in the correct place in the scene, we will not know, right? So I think the next thing to do is to extract the camera position, and then to actually implement the view matrix, and then we will actually figure out if, you know, if this is correct. Man, this is like more than 1% off of a non-uniform scale. Damn it. Okay, you know what? Let's just leave it to do comment for now. And I don't want to handle, you can handle non-uniform scale in our case by baking it into the geometry, but it breaks instancing, so it's like, oh, you know what I should just do? Yeah, forget it. We'll deal with this later. This is fine. Okay, so we need to extract the camera, and then once we extract the camera and actually change our code to be able to handle a view transform, we will be able to actually know if we have like further bugs to fix, right? All right, let me take a brief pause. So Luau is completely off topic for the stream. Roblox is completely off topic for the stream. This has nothing to do with Roblox. I haven't worked at Roblox for a year now, people. Stop like asking me about Roblox. I did play Roblox yesterday, but you know, I know people who are working on Roblox games, so I help them with that occasionally. But otherwise, that's kind of it. Yeah, so WXYZ is, so the thing about GLM is not even that. They can't decide, so they have two defines. This has boggled my mind when I found out. And like, I don't recall, we set up some of them. Oh no, okay. So we set both defines that are supposed to make the quaternion sane. Let me validate. Okay, this is important. Obviously quaternions, so there is like the matrix column row thing, and then there's the quaternion thing. And the quaternion thing is like even more insidious because it just completely changes the meaning in like more fundamental ways. With the matrix, at least like you transpose it. If it was a rotation matrix, it's just an inverse rotation. So it's like it's still a rotation matrix. With a quaternion, I mean, it is still a quaternion, but the rotation that it represents has nothing to do with the original one, as far as I know, at least. Yeah, so let me look at this because maybe this should be correct. God, okay, hold on. Okay, yeah, no. So the two defines that we said should correctly place the rotation. So this is correct then, or it should be. I'm pretty sure this function is correct, because I mean, like, it had bugs before, but I'm pretty sure I fixed all of the bugs. Rotation is in the right place, translation is in the right place, scales are fine. I'm pretty sure this is fine. This is good code. I like this code. Maybe this should be in cgltf as well, because maybe you need it, but maybe you don't. But the more important question is... Maybe this is all correct and the scene just looks very weird from a particular angle that we're looking at from. It is possible. The other possibility is that we could have bugs in our Culling code that just were not like visible before. But it looked really strange. I can use RenderDoc to look at this in the... It won't help much, but it just looked strange. It's like, so there's like these two houses. This camera might be like these chairs, right? They're all like rotated around each other, around some like random point in some really weird way. So this looks broken to me. I just don't fully... Like, I don't know why it would be broken. Let's just use a debugger to tell us. There was a question in chat, or not a question, like a comment about editors and autocomplete and all of the jazz. This is Zed, Z-E-D. This is an editor. I've been using it for the last 4 months or so. It uses Copilot, GitHub Copilot as an autocomplete, in addition to the more traditional autocomplete, which Kafka from the stream helped me fix, which was great. And yeah, and then the debugger is GDB, obviously. It has its moments. It's not ideal necessarily, but I don't have any other debugger. So, hey, I use what I have. So, no, hold on. I want... for people who didn't know that GDB can do this, we now know. This is called TUI, T-U-I, text user interface. And it's pretty decent in GDB. It's horrible in LLDB, so I would not recommend trying this on like Mac or whatever. But in GDB, it is great. So let's just inspect this. The difficulty is that I don't actually know exactly what like a translation or rotation or whatever should be because of the nested hierarchy. Whoa, that is funky. Hold on, what? Huh. Hold on. This is suspicious. Oh, damn it. The one problem with TUI is it kind of breaks the key bindings. Oh yeah, right. So the issue here is the whole level is like rotated at the root. And so because of this, the translations that you see, the local translations that you see in the nodes, like really don't correspond to the translations that you see in the world transforms, which just makes it a little bit harder to debug because you don't know if the values that you are getting are correct or not at all. But okay, so translation, rotation, scale. These are fine. The rotation is correct. It's like a 90-degree. So it's what would be necessary to flip from like a Y up to Z up or something like that, or like that way around, Z up to Y up. Translation, I don't know, but translation is the least likely component that would be broken. So this is all suspicious because while the scene really doesn't look correct to me, maybe I'm just imagining this. Like, this is weird. So, okay. Oh, the other thing that might happen actually, maybe now that I'm thinking about this, if the meshes are misaligned, so like if our mesh indexing is like wrong somehow, which it shouldn't be, but if it is, then you're gonna see really weird results. Okay, so there's only two things we can do. We can complete the camera and then fully debug from there, or we can use renderdoc to try to tell us what's going on here. Let me just double check a few things. This is the first mesh. This is correct. Has some transform. Okay. So I don't know. This code seems fine. I'm not sure about this now because like this seems like it should be correct, but maybe there's like a, oh yeah, sorry, I wanted to check if the reason why I started the debugger in the first place. Hold on. Let's do breakpoint and decompose transform and then run this. The other thing I don't like is performance, but we'll fix this later. Okay, so hold on. So what I want to do is draw. Yeah, okay, so the Quaternion definitely is messed up. This is why I wanted to debug. Okay, so orientation here is 0, 0, 0, sorry, 0, 0, like the axis, well, the XYZ components are, so the constructor, this constructor is messing up with our order, despite the fact that we have a bunch of defines set to like supposedly have that not happen. So it is WXYZ, despite the fact that it shouldn't be, which is confusing, but oh, there was a bug in GLM that was never fixed. Oh my god. Okay, I think there might be a function. Let me, like quad XY, quad something. Yeah, so there's this function that might work. I could just swap the arguments, but if this bug ever gets fixed, then my fix will be broken, like it's so terrible. Oh, that function does nothing. Wait, what the heck, people? Well, of course, because it goes down this path. But if this path is incorrect to begin with, man. Okay, if people do have a suggestion for math library replacement, I would take that suggestion eventually. So, wait, is that the define we are setting? No. Yeah, and the order was XYZW in the debugger. It's just the order was like correct from the naming perspective. The problem must be in the constructor. Oh god, is this like a third define? Oh, there's a third define. Okay, great. But something else might break if I enable this define. Oh boy. Okay. I remember this being a problem like throughout the development of this project. Every time we deal with quaternions, we discover that something inside them in GLM is like not ordered correctly, and then various functions expect various orders. Okay, so this is correct as much as, you know. Let me run the kitten again, because I'm worried that this, no, this looks the same as it used to. At least this kitten is the same, and this means everything else probably is. Okay, all right, so this was the define that we didn't have set. We will have to replicate this in the Visual Studio projects, which we still maintain for unclear reasons. Oops, sorry, hold on. Wait, what? Huh? Why was this empty? No, okay, all good. Okay. Okay, so this might be correct, and if it's just the camera is essentially at ground level inside some building staring forward, which, you know, is not conducive to good rendering results. So let me enable the define, because I will forget otherwise. And of course, the way that we are going to enable the define is just patching this in, because, you know, I can't even run Visual Studio right now. I should just remove all of this and just expect people to use CMake, but maybe later. Okay, so one thing I want to do now is I want to commit this code, because this is a good checkpoint. We don't have the camera yet, we don't have the view matrix, etc., but, you know, we haven't broken anything catastrophically. And we have achieved some progress, but not all progress yet. Okay. Initial glTF scene support. We now can load mesh data and no data from glTF files. Some restrictions. I should lift. It's fine. And run that instead of instance.g files. I think fundamentally, if you have three defines that you have to set to like make quaternions XYZW, like something is not correct. Like that is not the correct strategy of fixing this problem. Anyway, I am glad GLM exists. I just wish quaternions were better there. Okay, so cameras, and then I kind of want to fix this problem. So essentially, if you have a mesh with multiple materials, it's actually multiple primitives inside glTF. And what we should do, for now at least, is just attach kind of primitives individually as meshes to the node with the same transform. And this is not tracked. Yeah, we need like a re-indexing table for this basically. So what I'll do is I'll do I guess I'll just do wait, hold on. Yeah, okay, that's fine. I guess primitives. And then here we will remove this. There's not like a good way for us to test this right now. And then unfortunately, let's just do pi, because the only like asset that we are using right now for testing is the one where every mesh only has one primitive, but this part is very simple, so we'll just assume it works, and if it ever doesn't work, we can fix it. So the way this will work is we'll just say primitives push back, make pair. So this is correct even. And then we know we are appending this much. And this will add draw call, not draw calls, wait, this is not correct. Result something meshes, I called it geometry. Okay, I think this is correct. And then here we decompose, and then we do primitives. Fine. Okay. Again, there's no way to test this because we only have one primitive per mesh. But what should happen is that we just record the range of the mesh objects that we actually appended to the scene, and then whenever we instantiate a mesh, we just use that range that we recorded. And then for every primitive, we now create a draw call. Which means that technically, let me just... technically, the noun mesh now means different things. In glTF, it means a bunch of primitives. And in our code, in our scene code, it means like a piece of geometry with the same material. Which is different, but that's fine. Okay, so now we are ready to add some cameras. Why not cross-check why not cross-check the with a smaller model like flight helmet? We can. I honestly don't wanna like solve well. We can, like, there's no reason not to really, other than, you know, we don't have like a controllable camera, so I don't even know if the asset would render, but yeah, sure. We can actually do this. So this is kind of the problem, like, because we don't have a camera that points at a mesh, I don't really know. I have seen, I don't see like anything right now, right? Is it because we have a bug? Or is it because the default camera position is such that it points kind of away from the contents? I don't know. And we are going to extract the camera from the file right now. I don't want to implement like actual camera movement yet. But that means that the file that doesn't have the camera will still have the camera in this default position, right? So it's hard to know. Oh, and because we have culling, we can't even look in render doc because we are rendering 0 triangles, because everything there is to render, I'm assuming, is culled. Let's print some debug thing that just says, yeah, that just says this. So yeah, we loaded 15 meshes, we used 49 draw calls, but we're rendering 0 triangles. They're probably all off screen. So the benefit of using a larger scene is that it's more likely that at least one small part of the scene, even the one maybe you don't want, is going to be in view. Anyway. Yeah, let me, while we're here, let me just do a quick perf capture. And I think we'll load the camera and then we'll call it a day probably. Well, yeah, because the camera will need a bunch of fixes. So it's not just a matter of like loading the camera. It's a matter of adding view matrix support and stuff, which is not that hard, but like it's work that needs to happen. Unless I have somewhere, I might have some weird code in some shaders that like will fight me right now. Okay. Okay. Maybe this is just kind of what it is in debug. Let's switch briefly to release. I just want to see if the code is fast in release. It's faster. We are loading like a bunch of geometry. The issue here is we are doing simplification and meshlet processing and all of this stuff. This is eventually, it would make more sense to have this in like a separate binary that creates some sort of file with all of the level of detail data and all of the meshlet data pre-processed, which reduces iteration speed, so it's not always appropriate. But yeah, okay, anyway. It is tempting to eventually do that because waiting a couple seconds to start is not great. Okay, so camera. Okay. Let me look at the shaders that I have. Just, I want to like recall the math and stuff. Okay. Okay, so we have a bunch of math in the shaders in a bunch of places that basically assumes that view matrix is identity, which, you know, obviously you would never do this. It just wasn't a thing and we didn't have to fix that thing up until now. So what we need to do, what is the camera from the glTF perspective? If you look at the file, there is a camera here. It has a field of view, and then a bunch of other stuff that honestly I'm going to ignore. So the aspect ratio, it makes sense to specify this because if you look in Blender, if you see this frame like sort of that's a little brighter in the center, this is where the field of view points. So like ideally when we render, if we got the field of view correctly, then you'll see the exact same picture, except you'll only see the exact same picture if the aspect ratio is the exact same. Now we have a window that can be resized, so it would be inconvenient we can't, like, we could use the aspect ratio and do like letterboxing or something like this, but like it's all nonsense. Nobody's gonna do this, right? What we really have to do is we just take the field of view and then use the Windows aspect ratio. And then similarly, z-far, z-near, we could use them as is. I don't like doing this. Z-near is critical kind of for the it's kind of important for the z-buffer precision. Not really, because we use infinite projection matrix, but it's a little bit important. And like it's generally fine to leave it hard-coded, honestly. And then z-far, we have an infinite projection matrix, but we have a notion of this draw distance that's like how far do we have to draw. So, but like the most important thing that means from the camera is really two things. One is what's written here is the field of view, and then the other one is the transform matrix, which is not in the camera because cameras are attached to nodes. And so we can use the same code that we've just written to essentially extract the position and rotation of the camera, and then build the camera matrix, and then use that as our view matrix. So, with all of that said, let me create, eventually there's some refactoring that should happen on this code because, you know, because some things belong in like different CPP files and stuff like this. And there's some inefficiencies in the code that we would ideally correct and all of that stuff. But for now, I will just add a struct with the data that we're going to extract from the file. And then wherever we call load scene, so we'll have the camera, and then we'll default this to whatever we were using. We were using like 70, right? So glm 70, and then we will let the camera override it. Oh, not the camera, the glTF file override it. That's a very weird order. Okay. Okay, so whenever we have a node, that's fine. Oh, I don't think it's an else. I think you can have. This is where, so like, glTF is not perfect. For example, you can only attach one mesh to one node and one camera to one node, which means that if you want to attach multiple meshes to the same position, you have to either use these primitives, which is not really correct, or you have to have like these proxy nodes, which again for us doesn't really matter because we discard this entire structure to begin with, but there are some things that I wish people who were speccing glTF all of these years ago did a little bit better, but it's like very serviceable format. It's mostly fine. It's not ideal, but it's mostly fine. So we will, no, wait. We will assert that the type is perspective, and then there's nothing really else that we need to assert because we'll just use the field of view. Like there's no, oops, I guess there's like already a variable called camera. Okay, so this is in radians, so we don't need to transform it at all. And then position, and then orientation. Okay. Now, of course, extracting the camera is easy. Using the camera is slightly more difficult. we need to, well, there is this simple thing, which is here, instead of using a hard-coded value, we'll use the field of view. But really, the real thing that we need to change is we need to add a view matrix. Add a view matrix propagated through like all of the shaders and all of that stuff, right? So, oh yeah, so this changed the field of view from 70 to 60, so the camera is like a little bit more narrow now. Okay. The tricky, you would notice that I preserved quaternions, but here I'm talking about matrices. In the shaders, we mostly use quaternions right now, but there's only one matrix. Quaternions are nice because the quaternion plus position is like a more compact representation, and there's other nice properties about this. But for a view matrix, we could just propagate quaternion to the shader, but it kind of doesn't really make sense because there's only one that you need to pass to the shader, and so you're not saving much, and the transformation by quaternion is slightly more expensive. So what we're going to do is we're going to add a view matrix. For the projection matrix, we use glm's function to like build it. Wait, how does this even, do we do using namespaces somewhere? Interesting. Anyway, but for the view matrix, essentially we need to transform the quaternion to a matrix. This is where we will, and it feels redundant a little bit, right? We just went from matrix to quaternion and now we're going back. But I kind of like this way because this means that the actual representation is the quaternion, and then the matrix is just how you currently want to use this. But like you could just save the view matrix, etc. Either way is fine. If we implement code to actually rotate the camera with keyboard or mouse, then it's like, okay, it actually matters what you're dealing with a little bit more. So, okay, so there's a mat forecast thing that glm has that goes from quaternion to hopefully a matrix, and it doesn't compile because there's no, where is this? Wait, why would this not compile? Is this like an X or something? I guess this file is not included, but that's strange. Oh, GTC quaternion. Interesting. What the heck? Okay, let's see. Okay. Nothing is going to change yet, obviously. We aren't really using... Okay. Nah. So, and then we need to translate it, which is just a multiply, but I think glm has like a function. No, it does not. All right. So it has these transform helpers, but I guess we're not including those. Let's see. Normally this part would be way faster, but this is a library that I basically almost never used other than this project, and I mean, I could just use this one, right? Oh, it is in space. Okay. And then one thing you need to, well, it's not. Yeah, okay, hold on. glm GTX transform. I see. It's probably not a great idea to include all of these like this, but for now it's fine. Oh, it's an experimental extension and may change in the future. You know, this is stupid. Okay. Oh no. Oh, right, because it's in like 4. Yeah. Okay. All right. Who needs matrix math when you can just batch a freaking column and like forget about the issues? All right. So now, so we have this frustum planes, but these are in view space, so that is fine. Okay, so now we basically need to use this matrix. There's 2 things we need to change for that. So one is the actual transform. So if you look at our transform code, and we currently have 2 variants of the shader, one mesh shader and one for the traditional raster. We're going to be deleting traditional raster, I think, because I think we'll just require mesh shaders, just to keep us sane, probably. But for now, we support it. For now, it's useful to switch between them. So we have this global struct that currently has a projection matrix, and we use it here. So we'll just do that. We'll add a view space transform here. Okay, cool. Notice that I am putting parentheses here. These are important. If you don't put them in, you have a matrix times vector. If you put them in, you have a matrix times this. These are equivalent mathematically. They are not quite equivalent numerically, they're close, but this one is more computationally intensive because you have one matrix multiply followed by a vector multiply, and here you have 2 vector matrix multiplies. So this is faster. And this is like small things that you just have to constantly keep sort of in your mind as you are writing graphics code, because stuff like this like adds up. It's not a huge deal. It's not gonna transform the performance of this code, but it is slightly important, and it is more important on sort of slow hardware. We don't have slow hardware right now, but still good to be fast. So then I don't remember where this thing is declared. Yeah. So we will now have view projection, and then here we unfortunately need to repeat the view matrix, which is a little bit reductive, but redundant, but and then unfortunately we have to repeat this in C++ code because at some point I didn't want to deal with like the like issues of compiling the same code in GLSL versus C++, and maybe we'll have to deal with this at some point. So this is not great, but my recollection is that this is needed for the task shader. Yeah. All right. So we'll make all of this a little better. And I think we might be running close to the limit in terms of size of what we can use, practically speaking, for push constants. But let's just have... So this I fixed, and then our culling code is going to be broken. But let's look at what happens if we just run. Yay! We already have to solve this problem, which of course we do. Okay, that's fine. Let's not be wasteful then, and then let's get this from... This is like not very nice, but get the code working first, refactor later. Oh, yeah, hold on. I didn't view... Yeah, hold on. Okay. Well, clearly the code doesn't work. Oh, hey. This is I disabled like cluster calling. Is this directionally correct? This is not. This thing should be flipped, right? Anyway, let me fix culling code first and then we'll actually figure out. So I fixed the vertex shader and the mesh shader. But the problem is we also do draw call culling, we do cluster culling, and like everywhere where we had an assumption about coordinate space, we now have to incorporate the fact that we have this view matrix to worry about. So, so this is the compute shader. We unfortunately duplicated this code in a task shader. I've talked about all of this stuff on, I think, the last stream, yeah, the previous stream. We are gonna have to fix all of this because it's obviously unsustainable to keep like duplicating things like that. But, okay, hold on. But for now, I want to get this code to run. So that covers this, and then, oh yeah, I fixed draw call comp. There's another compute shader. Cluster call comp, yeah. Yeah, of course. View. Okay. Okay. Let's try this again. All right, this is better. Yeah, so clearly, let me flip between modes and see. So this is a little strange. This is fine. This is fine. This is fine. There's some minor. Interesting. Don't fully understand why one thing happens here. It's mostly fine. There's some minor bug because. But there's a minor bug maybe, but the bigger issue is clearly these perspectives are completely different. So first of all, the camera looks as if it's like underground. This is actually easy to check. Oh, the view, oh, of course. I'm sure there's a chat entry that says, no, you should not have done this like this. So this is wrong. This is not the view matrix. This is like the inverse view matrix. Yeah, and there might be one other thing that's wrong. It's still probably, I will actually pause to think about this. Yeah, okay. I think it's time to pause and think about this. This is actually, this should have been. So what I can do is I could use, I'm sure glTF has like a lookat function, but the lookat doesn't quite do what I want. No, this shouldn't. Man, I haven't done this like camera matrix math in like years. Hold on. So, interesting. I'm not sure. There's so many things that can go wrong with like matrix operations and stuff. But even the position is broken, and I'm not sure why that is. So I'm not sure where. Hold on, let me just try to. Oh boy. So our camera, oh no, yeah, our camera is, yeah, okay, so this might be correct position now because it's pointing. Yeah, okay, so I think what's happening is this. So, okay, pause and explain. The first problem was the view matrix is the matrix that gets us from world space to camera view space. The matrix that we built here was the matrix that's kind of the opposite. It's what you would use to render an object. So it's what gets you from the object space to world space. And what you want is the inverse of that. So that's the first problem. The second problem is there's different conventions in what view space is that apply in different renders in different places. I think in our render we have assumed that plus z, positive z, is in front of the camera. And I assume that glTF says it's the reverse. I don't fully know, like I would need to double check this. The way you fix this is you flip the z-axis. Something probably will break if I just flip the z-axis, but I will flip the z-axis unapologetically and then worry about this later. It's not quite that Vulkan uses, like we use a different coordinate system. So I think this might be the missing piece, but also things might be upside down if you just flip z. Like it's more correct to use, yeah, things are very inverted, obviously. Hold on. So let me go back to, yeah, things are like flip left to right and the framing is still wrong. The thing we should be matching roughly, right, is, I already talked about the aspect ratio problem. So this is kind of the screen at the correct sort of size. So things are flipped left to right, things are inverted, etc. This is all kind of expected because, again, as I said, it's not enough to do, it's not quite correct to do the transform that I'm doing by just flipping one axis. And if you only flip one axis, then you change the winding of the triangles. And it should be expected that things are incorrect. Oh, this is very broken. Hold on. Can I do... Yeah. The position should be in place. So essentially, man, this is painful to do on the fly. All right, let me... Wait, what? Hold on. Shouldn't this have worked? All right, I need to actually think about this. Let me pause for a little bit. It's been a speed run. Yep, already said that the winding order. Yeah, so no, yeah, I mean, like the coordinate space is different, which is fine. I'm not even sure what coordinate system glTF expects. I honestly never worked with glTF cameras before. And object defining projection parameters. Plus X is to the right. The lens looks towards the local minus Z axis, so this is the thing that we had to fix. And then the top is aligned with the local plus Y. I am confused as to what happened when... So this flips the winding. I'm confused as to what happened here because... maybe I'm mishandling the row column stuff in GLM, because this is just unexpected. Oh, whoa. Did I type it like this? Okay, that would explain a few things. Maybe more than a few things. Well, hold on. So, oh my God, wait. All right. So invert it, and after this patch the rows. I don't recall how this code, like, okay. Yeah, okay, so this is interesting. Why would, is that, oh, you might have to, yeah, you have to flip the column. Oh boy. Okay, so instead of doing this, we are going to I'm so worried about all of these matrix transforms because, like, I don't know, is this a pre-scale or a post-scale? And it's kind of like really important as to whether this prepends the transformation or appends the transformation. And if it doesn't do the right order, I should have done this first, then it's like clearly not the correct thing to do. All right. So this is, so then why would flipping X maybe this is not the correct thing to do. Is there not like an identity thing in GLM? This is so weird. Okay, identity. So okay, hold on. What does it expect exactly? Because I'm still not sure which order various functions in GLM do, like work in. Oh, yay! Of course it was the different order. Yeah, so the X, oh, we can't just flip X, the winding has to be flipped. Now I have to pause. So, I mean, you know, we could declare partial victory. Obviously, we'll fix the winding, but this is kind of the thing that we wanted to render, right? If you look at this left thing versus the right thing, then, you know, obviously, like, you don't see the floor. But the reason why you don't see the floor is you see the kind of back sides of the objects. We can fix this easily. The problem is the cone culling. I'm starting to doubt the conventions that we've used because because we've said Z was forward and Z is forward. Does like this guy flip something? Let me just re-examine. Oh no, we wrote this function ourselves. This function is a good function. It just sets, yeah, okay. And I should mention, so there's like different coordinate systems involved in sort of different renderers. It's not just a y up z up problem, it's also right-handed, left-handed, which direction in front of the camera is it plus z or minus z. I like the convention where in front of the camera you have +Z. And this aligns with the clip space convention that hardware uses by default. They're the, like you can flip anything with a projection matrix. So like if we put -1 here, then we wouldn't have to put the other -1 that we have put here. I'm not sure if this will work, but the complicating factor in all of this is that we also have the cone culling that we're doing, which was culling backface cones. And then also we have frustum culling. So like a bunch of things have to switch when you switch the conventions. So, but the thing I'm confused about is, so if we invert the culling right now, which we can absolutely do, other things would break. Why was OBJ rendering correctly is essentially the question. Is it just the case that glTF has... I guess glTF would have inverted winding. Would that make sense? All of this doesn't perfectly work because... Because yeah, like okay, I can switch winding and it will not work, or it will not work in isolation. It will work in isolation if I disable mesh shading, but if I don't disable mesh shading, then it will not work. Or it will. I'm now confused. No, hold on. Yeah, so if I disable mesh shading, things are fine, but if I don't, things have missing pieces. The reason is we are doing backface culling with task shaders, and that doesn't work. That's a little broken. Oh, I'm not applying the scale when I do selection. Okay, there's some stuff to fix in the future. But yeah, so I could fix the cone culling. But the bigger question is, so yeah, so what happens if I just fix the winding? Is that correct? That is correct. Yeah, okay. So really what I should do is I should go in my glTF loading code and flip the triangle winding. Because I think it's just the difference between clockwise, counterclockwise expectation, I guess, between OBJ and glTF. This is so weird because I didn't have to worry about this before, and I'm now questioning how anything worked ever before. Oh, right, so there's now a -1. Yeah. Interesting. Yeah. That looks trippy. So maybe what I should do is I should do counterclockwise and I should fix the culling math, and then you will never see the same kittens as you saw before because we now like flip the camera space to point to different directions and stuff, but it's fine. Okay, so then the thing I need to do then is wherever we do cone culling, which is this. This is just strange. So interesting. Oh, this is just completely broken. Hold on. So we have stuff to fix. We haven't finished fixing everything we needed to fix. This is also a world space entity, which needs to be transformed appropriately. And then unfortunately we have to repeat this. We should really fix this. Okay, so that. Oh yeah, because that just magically okay. I think we are good now. Okay, I think we are good. I think just flipping the orientation. It's almost surprising that that's just enough, but I guess that's just enough. Yeah, because there is no. Okay, yeah, I think we are good. All right, I think we are good. And then this is a little broken, but I think it's just a scaling problem, maybe. Essentially, we have all of these like automatic level of detail, and I haven't tested the level of detail stuff in a while on Bistro specifically. Wait, where's my window? And your expectation should be that level of detail basically doesn't change the visuals very visibly, and it generally doesn't, but there's two problems here. One is that the bigger one is that this arch thing like completely disappears, which like shouldn't happen. I'm not sure why that is. And then the whatever this tree thing is, the branches get like eradicated. But the way level of detail selection works now is just completely automatic based on the error that the simplifier returns. And then I'm now thinking maybe I forgot to multiply something by the mesh scale or something like this. The thing about the scene now is I think the mesh scale is fairly high. Let's print a couple of values somewhere. Because yeah, I'm doing this thing, but this thing is like not enough if the runtime selection doesn't account for this. Actually, hold on. Oh no, I do take scale into account. So this is now in view space. And this is now in view space. Maybe it's a simplifier bug. That would be a very strange bug. Like it's not. It's not what I would have expected at all. Huh. All right, I'll need to debug this specific part later. This might be like a thing that should be improved in Mesh Optimizer. I'm just surprised to see that. Oh, that thing looks like a pruning bug as well, maybe. All right, so there's like minor stuff to fix, but in general, this is kind of where I was hoping we would get to. We have a scene. And it's taken us very little. Let me compile and release so that we render without like validation layers and all of that jazz. Yeah, so there's like minor LOD bugs that I'll need to investigate in the future. Our CPU time. Oh, we have vsync enabled. Let's disable vsync. All right. So our GPU time is like 0.7 milliseconds. There's just not a lot of geometry to render. Again, like we used to work with a scene that was whatever that scene was. like billions of triangles, and then we call it, and then we load it and stuff, and then we get to an acceptable tens of millions of triangles to render. Here we have 1.7 million triangles without... I think there might be some other forms of culling actually that are broken right now, because maybe that's fine. I would have expected a little bit better culling rates, I guess. There might be something. Hold on. It's sometimes hard to like think and talk at the same time. Let me pause and think about this. Oh, we should fix triangle culling, by the way. We have this mode that we aren't really using that culls individual triangles, and I believe that mode is hardwired, to do backface culling on, like, you know, the winding that we just flipped essentially, which is obviously wrong. So we are gonna fix that here. Which you don't really need. On this GPU, it doesn't really help to do culling in Mesh Shader, but we have this mode, and it's substantially reducing the number of triangles we render to be even smaller. It's just that the GPU time is still the same, because it's an optimization that you don't need on this GPU, but you do need on the on weaker previous generation AMD GPUs like RDNA 2. So, okay, what is confusing me now? The only thing that's remaining that's confusing me is the culling efficiency. The last thing we'll do before we end is we'll just load this in render doc to just look at the render doc, like rendering and how that looks in wireframe, essentially with occlusion culling enabled and stuff. But yeah, it's interesting that I've never worked with this scene before, so I don't have a good intuition for the view that we are looking at right now. Is it like most of the stuff? Oh, we actually picked a view that's, so like some stuff is outside of the frustum, right? Like objects here are not visible, objects here are not going to be visible, but like everything here is going to be visible. And also I think Blender, there's some weird mismatch that I saw between glTF export and the stats that Blender shows. I have reasons to believe that the Blender stats are slightly incorrect. For example, right now Blender says, oh hey, this entire view is 1.7 million triangles. That's like clearly not true, because oops, wrong command line. Because if we disable level of detail and then disable culling, this is not how you disable culling, disable cluster culling and stuff, we render 2.6 million. So I think the whole scene was like more like 3 and something, which we render 1.3, and then with LOD we render, wait, oh, I see what happens here. Yeah, so this is a simplification bug. That's annoying. I thought I fixed all things like this. Right, this geometry shouldn't even be there. Huh, interesting. I haven't seen that specific thing before. Okay, I will investigate this separately. This is not a bug in this code. And of course there is some other stuff that you see where like LOD switching doesn't, like, you know, there's some edges and stuff that like change a little bit here, which is all fine. LODs aren't perfect, but they're getting better and better and better every release. Yeah, this stuff is challenging because the level of detail error thinks all of his triangles are very thin. And so this makes sense to me, the fact that this disappears. This doesn't. This is odd. But okay. All right. Anyway, I think we are in a pretty good spot. I'll spend the next 15 minutes if people have like questions, and I haven't looked at chat in a little bit, but if people have questions about what we have done, about how things work, maybe I forgot to do something, but I think we are in a good spot. We haven't loaded textures and materials, right? Which is something that we will do unless something happens. I should have time next Saturday. So probably next Saturday we can do texture loading with bindless. Yeah, texture loading itself should be quick. And then bindless, I'm not sure because I've never used the extension, but it's probably not too bad. So we might get to bindless and textures next week. But I'm not 100% sure yet if I'll have time. It kind of depends on stuff. So we will see. But yeah, other than that, and the LOD bug, that is a little unfortunate. Yeah, so let me load this in RenderDoc, and then I'll look at chat. And see if we'll have any final questions to answer. Okay, RenderDoc. And then here, and then distro. And then obviously I will push the code momentarily, and then you can like watch the stream, the recording of the stream later and all of that stuff. So the thing I'm curious about mainly is just the wireframe, because there's not much else to look at in RenderDoc. This is hard to look at. Yeah, there's so much thin geometry here that's making it difficult. I think the if I look here, there is this tree that I can't select. Hold on. Aha, yeah. So this tree has a bunch of triangles here, and it sort of looks like occlusion culling works reasonably well, because you don't see this. We can also like just disable occlusion culling at runtime and see if that has an impact, which it should. Yeah, anyway, so things mostly seem to work. The LOD bug is annoying, man. I thought this stuff doesn't happen anymore, but something is bugged here. It's also possible that just the criteria for selecting the level of detail is broken, but it's also possible there's a real LOD bug. Not bug, like it's hard to guarantee that stuff like this doesn't happen, but some mesh in the scene has a bad level of detail generated. But most of the stuff is fine, and the triangle count reduction is substantial with automatic settings, so that's good. I guess there is two things. This thing is a little weird. Yeah, there's one like obvious bug. Okay. All right. So oh yeah, occlusion culling. Sorry. So I think it's O. Yeah, so occlusion culling is a substantial reduction in geometry, and then a small improvement in performance. The performance is going to change because right now it's not much geometry. We don't sample textures. We don't cast rays from the fragment shader, which we might want to do. We'll see. I haven't thought about this yet. So there's like performance characteristics are going to change significantly, but the geometry reduction from occlusion culling is pretty good here, at least. Okay. Anyway, that's about it. Let me see. I haven't thought, so there's a question about restore. How do I put this? I have a general desire to experiment with ray tracing, but I don't have concrete plans, right? So I suspect next week it's gonna be just let's actually do one thing because I'm curious about one thing. But I suspect next week it's just gonna be textures and bindless. If there is a stream next week, we will see. And then which would be nice because we can render like a decently shaded scene from just, you know, directional light. Because there is normal maps on the scene which we don't have access to yet because we don't have textures. But then with ray tracing, then, you know, like we need to put the geometry into the BVH, we need to look at tracing array for like directional shadows or something like this. But eventually it might be interesting to get to the place where we can do a bunch of effects with ray tracing. For example, the scene has reflective objects. It would be cool if the reflective objects had reflections. The scene has reflective objects with roughness, and so it would be nice if reflections were diffuse. The scene has lights, and it would be nice if lights cast shadows and stuff. So like, in theory, we might want to do more than one ray per pixel. And that's where it would be very nice to have some combination of temporal accumulation, spatial accumulation, and denoising. And this is where we might get to restore, but I don't know, right? I think to get there, we need to first do like 5+ streams of like work, and then maybe we'll be like at the point where we say, oh yeah, actually now the next best thing to do is restore. So we'll see. UI in games is usually not really rendered with like Vertex, with vector graphics. It's usually just a bunch of texture, like quasi-texture geometry. There's some cases where that's not true anymore. A lot of games now tend to ship with Slug, which is a middleware to render fonts, and also some vector graphics, but I think it's mostly fonts. And that middleware is doing kind of vector graphics, like it's using triangles, but it has fragment shaders that essentially compute vector sort of curve coverage, which is more vector graphics at this point, right? But a lot of games still use quads with textures. If we end up integrating DRM GUI or something like this, that just uses quad rendering. It's not like complicated from this perspective. Yeah. So one thing, I'll look at chat in a moment again. One thing I just was very curious about was, oh, and we'll also need a stream at some point. I think it might be that next week, if the stream next stream, let's put it like this, next stream we might do bindless and textures, but then we might have to have a stream where we just like refactor code and throw out like garbage we don't need and like stuff like this, because obviously yeah, okay, so this is just normal. This is not transformed in any way. Oof. Yeah, hold on. Since we are fixing issues with coordinate spaces anyway, we might as well do this. One thing, as I said, we might just delete the traditional raster at this point, because whatever, it's just a pain to, maybe we'll find a way to refactor code so that we can keep it, but yeah. So what I was curious about is yeah, this is right actually. I'm not sure where. I'm not sure what the sun direction is. I don't know. Okay. All right. Okay. Pretty decent. Yeah, there's a couple of things with level of details that annoy me. But this, there is one that's like, shouldn't happen. All right, let's see, any final questions? So, I mean, we'll start with just shadow mapping by, not shadow mapping, but like shadow tracing, I guess, by casting like array, right? This is going to be the baseline, but because we have a scene that has normal maps and it doesn't have roughness technically maps, it has gloss maps, but that's fine. And also, I don't think this file has them, but if you look in Blender at this view, you'll see these lamps. I don't think these lamps have like actual light sources in them right now from the glTF perspective, but like I'll see maybe there's a version of the scene that has the light setup. In theory, right, you could imagine doing the thing I was talking about in the beginning, where you have you like do importance sampling, you find the light sources that you want to trace the rays to, you use the rays to check occlusion status so everything can have shadows, and then based on like BRDF properties you do like the rays that are not just in the direction of the light, but like whatever, right? you can complicate this, you can take this arbitrarily far. I don't know how far we will take this. Obviously we will want to render at least something of basically this quality, right? This is like the minimum bar, but the maximum bar is kind of unlimited, so we will see. It's been, I don't want to go too deeply into like math involved in BRDFs and stuff. I don't think I'm the best person to do like streams like this about PBR math, but I think the to the extent that we need this information to do a more complicated ray tracing setup might be interesting to do. We will see. No promises, but it might happen. All right, we are closing on the 3rd hour. It's been pretty good results, emissive materials, yeah, all of this. I plan to not handle shader materials to the extent that I can afford to. So the bindless setup will allow me to have no shader splits because of the bound resources. And then there's a question of BRDFs. You usually don't need, how do I put this? You might be able to get away with having very few shaders in production. Doom renderer is a good example of pushing visuals with very few material types very far. Having said this, you might want more than one, right? We have one right now. There's ways to render. It is easy to change our current pipeline so that it can render more than one material type. There is some issues that are more annoying and more problematic, but it's not just a shader type. For example, so if you look here, these glasses that actually Blender right now shows as opaque, these are actually not opaque, these are translucent. We don't have support for translucency in our renderer. We don't have support for anything in our renderer. But to actually do that, you have to do certain things. For example, you can't do occlusion culling from these objects. So you have to split these in a separate paths anyway, etc. Right? So like for a lot of this stuff, you kind of have to separate more than just the material, more than just the shader. And then in terms of the shader that you're using, I think you can get reasonably far with just having one. I don't know how far, but I definitely wouldn't want to do more than like one shader until I have to. And again, there is production renderers that get a lot of mileage out of having very, very, very few shader types. My recollection was that the 2016 Doom, and I guess they did a presentation in 2018 or so. I think they quoted some number like 300 PSOs or something like this. And they did shadow maps and stuff. So like it's like the grand total. It's not just for the scene. So you can do a lot with very little. And how far you can go with this, we'll find out. Definitely don't plan to do more PSOs until we have to. Yeah, it's kind of like an Uber shader. The good thing about the glTF model is that it's kind of standardized material types for the most part. But now again, like, you know, it's maybe that just stops working at some point. We'll find out. Bindless helps because it means you don't have to bind extra parameters to the shader. And then there's a question of divergence, and then there's a question of other performance issues. And then there's some other questions. There's like a bunch of complicated stuff. I haven't even decided yet if we are gonna do tracing, how we're gonna do tracing, I'm not sure, because there is implications with denoisers that are complicated. You might want to do a G-buffer pass, and then lighting, and then shading, and that's good from a certain perspective, but that complicates things from a certain other perspective. So I'm not sure. I think we're going to keep things as simple as we can possibly keep them for as long as we possibly can, but then we'll see. Yeah, you can use one-by-one textures. Branches are branches are bad in shaders in certain cases, but I think a lot of the permutation explosion that we've seen in the past is also due to people like designing for the older GPUs, with the older GPUs in mind, where branches were more expensive. So there is like a bunch of possibilities. It can become unmanageable at a certain point, especially if you have complex shadowing setups. But because we will not have shadow maps at all, we will have different problems. I'm just not sure how different they are going to be. Anyway, that's kind of it. So this is the beautiful image, which is not so beautiful, but you know, baby steps that we are going to end with. This now has a lot of aliasing issues that bother me, but that's a problem for another day. Thank you everyone who attended the stream. So again, I'm not sure if there is going to be a stream next Saturday, and if there is not going to be a stream next Saturday, there might be a longer gap. We will see. But you know, however you found out that this stream happened, you will find out through the same channels. And until next time. The texture stuff is like important for not having draw call explosions, not the permutation explosions. But there's also, anyway, we will talk about all of these problems some other time. All right.